Welcome. I'm Ms. Mixella, and I'm one of the teachers at Eagle Crest High School, and this podcast is going to focus on an introduction to Young's Modulus for the Material Science Engineering class. So our essential questions for today is what's the relationship between stress and strain, and how can we use the stress-strain graph to infer the properties of a material? There is guided notes that should be linked in Schoology to this assignment. I would encourage you to pause and take notes as you listen. So to review, elastic deformation is caused by the stretching of bonds between atoms. Deformation of the material is reversed when the load is removed. So again, elastic deformation is not a permanent change. This is when the bonds are being stretched between the atoms in the material, but when the load is removed, it returns to the original position. In other words, the material returns to its original shape. Whereas plastic deformation is caused by the atoms' bonds breaking, generally at dislocations. This deformation is permanent and remains after the load is removed. So when something is plastically deformed, the material's shape is permanently changed. And again, we can see a nice illustration of that on the animation. That is caused by the breaking of bonds at dislocations within the material. So today we're going to explore Young's modulus, or a stress-strain graph, which is a way to mechanically test the properties of a material. Young's modulus is identified as capital E, and it is a measure of the elastic deformation equal to the ratio of the stress acting on a substance to the amount of strain produced. It's used by material scientists to predict the behavior of materials upon the impact of force. And it's very important to be able to predict how much force a material can withstand before failure. Examples of ways in which engineers look at this is cars. You want to examine the impact of force very carefully when engineering and designing a car, or bridges, as cars and trucks and other heavy loads are being repetitively driven over it. And it's tested using a tensile force, which we'll explain what tensile force is in just a minute. So tensile force is a pulling force that stretches the material. You can see with the tensile force we're pulling or stretching the material, and right now, elastic deformation is occurring. The moment we remove the tensile force and it won't return back to its original shape, we now have plastic deformation. And clearly we can see some necking occurring right here where there's extensive plastic deformation and the material is about to fail. So take a second and draw this blank stress strain graph into your notes, or if you're using the guided note sheet, it should already be there. And we're going to start to examine each section of the graph and add in some detail. The first section of the graph you might notice is the linear section of the graph. So if we look at where it is behaving in a very linear manner on this graph, that is the section of the graph where we can calculate the Young's modulus value, or the elastic deformation. Right here at this boundary, we are no longer behaving in a linear fashion. Elastic deformation ends, and now we are in the plastic deformation section over here. So to calculate Young's modulus, again, we're measuring the resistance of a material to elastic recoverable deformation under load. We would look at the rise and the run. And if we look at the linear section of the graph and calculate the rise and the run, the slope of the graph, or rise divided by run, would give us our Young's modulus value. Note right at the end of this linear section is a point that we call yield strength. Yield strength is the point where elastic deformation ends, and we're now going to have the material be plastically deformed. So the yield strength is defined as the maximum stress that a material can withstand before plastic deformation. Now let's examine the second part of this graph, where we no longer have a linear behavior. Now we're in plastic deformation. So when our line starts to curve and no longer acts in a linear fashion, this is the plastic deformation portion of the material. And we can see there's a couple of sections. Where that line reaches its highest amplitude is the difference between where it's being work hardened versus where it is beginning to neck. And we'll see an example of what that looks like in a bit. And then obviously fracture is where the material fails and breaks. So in the linear section of the graph, our material is being elastically deformed. The bonds are being stretched, but it would return to its original form after the load was removed. If we look in the plastic deformation section of this graph, we are now getting to where the material is permanently changing shape. After the load is removed, it will no longer go back to its original shape. And in the first part, we have work hardening or strain hardening. This is where the bonds of the atoms are being broken, the material is slipping at the dislocations, and that is a permanent change in its shape. And after this highest point along the line, we start to see necking occurring. And this is where we're seeing visible signs that the material is about to fail, right? And at some point it does, and we get the fracture. So ultimate strength is the maximum stress that a material can withstand before failure or fracture occurs. In other words, the ultimate strength point is the highest amplitude of the curved line. Failure is when the material no longer meets the desirable or intended objective. In other words, this entire section we would call the material as a failure. You can't depend on it anymore. Once it starts to neck, you would no longer be comfortable driving across the bridge, right? So that would be considered a failure of the material. And then fracture is when the material actually breaks or separates into two or more pieces. So if we examine what's happening at the atomic level, I would strongly encourage you to put this into your notes and draw some pictures here. In the elastic section, where our Young's modulus stress-strain curve is linear, we are seeing the atomic bonds being stretched. You can see here they are when the tensile force is pulling them, and they're being stretched, but they're staying in their positions. Whereas once we go into the plastic deformation section, those atoms are actually slipping. The bonds are broken at dislocations and the atoms are slipping, right? As dislocations start to pile up, your material is going to experience work hardening. Because if you remember, when we talked about dislocations, we talk about that eventually they get pinned or stuck. And so your material is getting harder and harder as those dislocations pile up over time. And so this is its ultimate strength value. This is the highest amplitude of that curved line. If we go over to the y-axis, it's going to tell us the amount of stress in megapascals that material can withstand before failure and fracture start to occur. And then once we pass that point, the material is now failing. We're beginning to see necking. We would no longer be comfortable using it as intended. And eventually it will rupture or fracture. So how does the stress-strain graph show the properties of a material? We're going to look at about 5 vocabulary words, many that we've used before. And and examine those. So take a second, please, and write each word in the definition into your notes, and then we'll talk through them. So when we measure strength, this is referred to as ultimate or tensile strength. We're measuring how much stress can be applied to a material before it permanently deforms or breaks. In other words, strength is how difficult it is to break something. And it is measured by the amplitude on the y-axis. The higher in amplitude it is, the stronger the material is. So as we can see on our tensile stress strain curve right here, the highest amplitude on the y-axis would occur at this point right here. And if we trace it over to the y-axis, we can see that this material would have an ultimate or tensile strength of 450 newtons per millimeters squared. Stiffness is different than strength. So please know that it's a big misconception to assume that stiffness is the same as strength. Stiffness measures the tendency of a material to return to its original form after being subjected to a force or a load. So in other words, stiffness is how difficult it is to be plastically deformed, how likely the material is to return to its original form after a load is applied. Stiffness is measured by the slope of the linear portion of the stress strain curve. In other words, the Young's modulus value, where we measure the slope of the line, is also correlated with the stiffness of the material, right? The slope of the linear or elastic proportion of the stress strain curve tells us the stiffness of the material. And stiffness is due to bond type. Certain bonds have a stronger force of attraction and can withstand that being stretched better than other bonds. So the stronger the bond is, the stiffer the material is. If we look at our graph on the right with two stress strain curves, one for material A and one for material B, we should see that material A has a much steeper slope for the linear section than material B does. And so material A would have a greater stiffness than material B would. Hardness is something we've done in a lab previously. When we did that lab, we measured the resistance to denting upon a compression force. So note, you cannot use a stress strain graph to talk about hardness. We cannot infer the hardness of a material by looking at a tensile graph. It's not measured using a stress strain or a tensile force. So one of the common misconceptions is to assume that if a material is strong, it's also stiff and vice versa. Let's look at an example of that with glass and a spring. Glass is difficult to bend. It's extremely stiff, but it's very easy to break. It's not very strong. So stiffness again measures the resistance of a material to a load being applied. You could add a weight to the top of a glass table and it's not going to sag under that load. It's difficult to bend, but it doesn't take much force to break it. So its strength is very low. Whereas a spring is easy to stretch and deform it, but very difficult to break or fracture it. So its stiffness is very low, but its strength is extremely high. So let's practice with those properties and using a Young's modulus or stress strain curve. Take a second and describe how the stiffness and strength of the three types of steel would compare. Hopefully, you remembered that stiffness is measured by the linear portion of the stress strain curve. So we can see for all three of these materials, the linear portion of the stress strain curve has the same slope. It would have the same rise over run value. So all three types of steel, high tension steel, high yield steel, and mild steel, would have the same stiffness. They respond to a load being applied in the same way. But they do have different strength values because ultimate strength is the highest amplitude of the curve along the line as we compare to the y-axis. So high tension steel is going to be stronger than high yield steel, which is stronger than mild steel. If we're ranking them, it would go high tension steel is the strongest, then high yield steel, and finally mild steel. All right, let's examine a couple of more properties. How does a stress strain graph show brittleness? If we remember from previous classes, we define brittle as being able to break with little to no energy absorbed when stressed. So that's shown when a stress strain curve has no or a very tiny plastic region. In other words, if there's no plastic region or the plastic region is extremely small, the material is very brittle. It breaks and fractures without the ability to be plastically deformed. Brittleness is based on ionic bonds. When ionic bonds slip, they create repulsion, and repulsion means that the material fractures or breaks. So we can see that this material that is the red stress strain curve is brittle. It fractured very quickly. There is very little plastic deformation. Most of the stress strain curve is linear. There's only a very small section of plastic deformation. Whereas our purple material is not brittle. In fact, the opposite of brittle is ductile, and we can see it's extremely ductile because it has an extensive plastic deformation section. It can be plastically deformed for quite a long time. You can see in the pictures below, when they fracture, a brittle material fractures in a very different way than a ductile material fractures. So when material science engineers look at the failure of a part, they can deduce a lot of things about the materials, the properties of the material. So again, ductile is the ability of a material to deform under tensile stress. So a ductile material has a long and extensive plastic region. And hence, I would not only draw an example of this long and extensive plastic region, but I'd even draw in a picture of what the failure looks like between these two different properties. When we refer to plastic, we're referring to the ability of a material to undergo permanent deformation under the stress curve without cracking. In other words, if something is plastic, it has little to no elastic region, very little linear region, but an extensive plastic region. And so we can see an example of a brittle material, a material that has an extensive elastic region, but no plastic region. An example of a ductile material has an extensive elastic region, but also a very long plastic region. And an example of something that's plastic, a very, very small elastic region, but an extensive plastic region. Again, the type of fracture that occurs determines the property of the material. So we can see that A would be the type of fracture we'd find for a brittle material. B would be the type of fracture we find for something that's moderately ductile. There's some necking that has occurred. Whereas C is the type of fracture we'd find for something that's highly ductile. There's extensive necking and plastic deformation. All right, let's practice and see if you can apply what you know. Rank the following materials by using the color of the line to identify them by their stiffness. Well, Hopefully remembered that stiffness is measured by the elastic or linear portion of the Young's modulus line. And so the blue line has the greatest slope and thus the highest stiffness, then red, then green, and finally purple would be last with the lowest slope. Again, stiffness is how the material responds to a load being applied. All right, let's rank the following materials using the color of line to identify them by their strength. Hopefully you said that the one with the highest strength based on the amplitude on the y-axis was the blue material, then the red material, then the green material, we'd be measuring from the highest point right here, and finally the purple material. Brittle materials are designed based on ultimate strength, the point at which they break or fracture, whereas ductile materials, engineers generally design and use materials based on their yield strength, this point, because for ductile materials, they don't want any of this plastic deformation to occur. All right, classify the following materials using the color of line to identify them as brittle, ductile, or plastic. Hopefully you told me that both the blue and red materials were brittle. The green material is ductile because it has an extensive section of plastic deformation. And the purple material is plastic in nature since there's very little linear portion or elastic deformation. Okay, as we read and interpret this graph to do a little bit more review, please note that this line is A, this line is B, and material C is actually right here, and then it goes all the way over to here. So C starts right here and then goes across, and then D and F I think are pretty self-explanatory. So if we look at this graph, which material is the strongest? Hopefully you told me material B, because its ultimate strength or the highest amplitude on the y-axis, it is stronger than any of the other materials shown on this stress strain graph. Which material has the highest stiffness, resistance to being bent when a load is applied? Hopefully you told me material C, because the elastic portion or linear portion of the stress strain curve, we have the steepest slope over here at material C. Which material is the most ductile? Well, remember, ductility is the ability to be drawn into a wire. And so we're looking for the one that has the most plastic deformation, which would be material C.